So let's go for the first example here, people. For the first example, we have a boat. So let's say there is a boat somewhere like this, and it is floating on the surface of water somewhere there, and there are two people standing. There is a person standing on the left end of the boat. Let's call this person A, has got a mass of 50 kg, and there is a person standing on the right end of the boat. Here, let's call this person B, has a mass of around 60 kg, and the boat itself is uniform. So it is given that the boat is uniform, has a length of 4 meter, has a mass of 40 kg. So these are the things that have been given to you in this particular problem. Now, these two people who are initially standing at two different ends of the boat, they want to talk about something. So they start walking towards the center, and they meet at the center of the boat. So these two, or A and B start walking on the boat, and meet at the center. And you need to find the displacement of the boat in this process. Take 2 minutes. So if you get something of this kind, if you get a problem of this kind, you have to first of all look at the entire object and choose a specific system. Now there are interacting objects. A is interacting with the boat, B is interacting with the boat, and as A walks, A will exert a force on the boat in the leftward direction. As B walks, B will exert a force on the boat in the rightward direction. And I'm guessing that because B is heavier, the force applied by B on the boat may be larger than the force applied by A on the boat, and maybe the boat should move to the right somewhere. So I have a few guesses about this situation, but still I have no clue what is the force exerted by A on the boat or force exerted by B on the boat. Further, A will have to initially speed up, and then A will have to slow down. B will have to speed up, and then B will have to slow down if they have to stop at the center. So the forces by A on the boat in general will be variable, forces by B on the boat will be in general variable. So when you get to a problem of this kind, now here we know that because this particular chapter is going on, this is from this chapter, and we should try to solve it using ideas in this chapter. But even if you get this problem standalone, you should immediately understand that doing this using force approach is hell. So let's not do this using force approach. Let us use some other approach. So what I'm going to do is I'm going to take A, B and the boat as a system. So then what happens is the force of interaction between A and the boat and B and the boat, these two forces become internal forces of the system. And internal forces don't change the acceleration, or don't lead to the acceleration of the system. They don't change the velocity of the center of mass, and so on. So that will make my analysis simple. I can probably ignore the forces acting between A and the boat and in between B and the boat. So for the solution, what I'm going to do is take this figure and take A plus B plus boat as the system. So my system is defined as A plus B plus boat. And for this system, because there are no external forces, no net external forces, there are external forces. Along the vertical axis, you will have weight, that's due to the earth, and then you will have upthrust, that's because of the water here. And these two forces will be equal and opposite, so they will nullify each other. Horizontally, there are no forces on the boat. So we will have zero net forces on the system. And if there are zero external forces, zero net external force, then the center of mass should not accelerate. So now you know that for this system, A plus B plus board system, acceleration of center of mass is going to be 0. That means the velocity of center of mass is going to be a constant. But I know that initial velocity of the center of mass, so V of center of mass, initially was 0 because everything was at rest on that lake surface. So this implies that V of center of mass finally should also be 0. That will mean that the displacement of the center of mass along x-axis is 0. So this is the entire chain of thoughts. Now how do I accomplish this? Two ways to do it. One is using the diagram and the other is using the formula. So I will show it to you first using the diagram. So let's try to locate the center of mass. Let's say for the boat, where will be the center of mass? For the boat, the center of mass will be approximately at the center of the boat here. Not approximately, exactly at the center because it's a uniform boat. So assuming the left hand side as x is equal to 0, I can assume the left hand side as x is equal to 0. I get the center of the boat as x is equal to 2 and the right hand side of the boat as x is equal to 4. I have got the x center of mass of the system as m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. So this will give you 80 plus 240. So this is 320. 320 by 150, 32 by 15 meter. And this is the x coordinate of the center of mass, which is greater than 2 meter. So you know that the center of mass should be somewhere here, slightly to the right of boat's center of mass. So what do? Let me take this system, go down and show you what will happen. So now let's assume for a moment that these two people, they meet at the center and the boat doesn't move. So the assumption is that A and B move. In fact, I can make it go here. Yeah. So the assumption that I have made here for the second figure is that A and B move and meet at the center of boat, while the boat does not move. So let me make that assumption and see what happens. So finally A will be standing at the center somewhere. He is right there. B will also be standing right at the center of the boat. That is it. So the center of mass of these two guys will be right at the center, and the center of mass of boat is also present there. So this place will be the x center of mass of the system, which will now become 2 in the axis system that I have taken. The left hand side is still x is equal to 0 and this point will still be x is equal to 2, and the blue dot, which is showing you the center of mass of the system, will be overlapping with the center of mass of the boat. But that means that the blue dot has shifted. But I know that the blue dot that represents the location of center of mass should have a 0 shift. So that means what happens is, as these two people come together and they meet at the center of the boat should itself shift in one direction. And how will the boat shift? The boat will shift in such a way that this blue dot, the new blue dot, coincides with the old blue dot. And that situation will be something like this. Yeah, you see that now the blue dot coincides with the old, sorry, the blue cross coincides with the old blue cross. So what happens is, as the two people come to the center of the boat and meet up, the boat itself shifts a bit to the right, so that finally the location of center of mass on the boat, which is the center of the boat, coincides with the coordinates of the point where the center of mass should be, which was that blue crossed point. So the shift should be the distance between these 2 points. The distance between these 2 points is 32 by 15 minus 2. So therefore delta x is 32 by 15 minus 2, that is 2 by 15 meter, or 0.3333 or 0.1333, sorry, which is 0.1333 meter with a bar on that 3. So this is how you can do this using a diagram. You can just think about what happens to the system if the boat doesn't move, and where does that center of mass go, and then because the center of mass should not go there, it should be back to this point where should everything be shifted. So something of this kind. But how could we have done this using the formula? So using the formula, let us try to do this particular problem. Let's say as A and B move. So what figure do I have? Yeah. Let us say as A and B move, so A moves to the right by 2 meter on the boat. B moves, so this is a lighter, different way. Yeah. So A moves 2 meter on the boat, B moves 2 meter on the boat, and let's say the boat itself moves, and we have no clue what is the direction in which the boat moves. So maybe one of you assume the boat to move to the left hand side by some amount x. So boat moves to the left by an amount x. And let us take some axis system. So let's say along the right hand side is the positive x-axis. That's the usual x-axis that we take. Now we will use that formula. We know that for this condition to be true, delta x of center of mass to be equal to 0, we have m1 delta x1 plus m2 delta x2 plus m3 delta x3 equal to 0 for a 3-body system. So we will use this formula straight away here, and you have got maybe m1 is this guy A, so 50 times delta x1. What is the change in x coordinate of the red guy? Plus 2, because he moves 2 meters towards the positive x-axis, and minus x because he moves minus x towards the negative x-axis by virtue of being on the boat. Then this guy B, so we have got 60 for him, and for him the x coordinate decreases by 2 because he moves leftward on the boat, and another decrease of x because the boat itself moves to the left by x. So minus 2 minus x plus 40 for the boat, and the displacement of the center of mass of boat itself, not of the system, of the boat itself, is x to the left. So minus x, and all that should be equal to 0, and this will give you 100 minus 50x minus what is that, 120 minus 60x minus 40x is equal to 0, or 60, 40 is 100, 150, and that goes over to the other side. This is minus 20. So minus 20 is equal to 150x, or x is equal to minus 2 by 15 meter. So what does the minus signify? The minus shows you that you have assumed the wrong direction for boat's displacement. The boat does not get displaced towards the leftward direction, it gets displaced in the rightward direction. So these are two different ways in which you could have attacked this particular problem. For the next example, what we have is a balloon, hot air balloon. So let's say there is this hot air balloon, and there is a string attached to this hot air balloon, and at the end of the string there is a man hanging on to save his life. So this is a man of mass small m, and this balloon itself has got a mass capital M, and the string has got a length L, or the rope has got a length L here. Yeah, so the rope here has got a length L, and the man is hanging on here, and maybe at the top there is a basket, and he will be safer if he is inside the basket. So what he wants to do is he wants to climb up and he wants to get into the basket. So he pulls onto the string or the rope and starts climbing up, climbing up, climbing up, and by the time he reaches this place where the basket is, so this is the place with the basket, you need to find out what is the distance that the balloon has descended by in the time that the man reaches the basket. So by what distance does the balloon descend in the process of man climbing up to the basket. And if it helps, I will also mention that this hot air balloon and the man and the rope and the basket, everything is hanging in air somewhere. The same thing. So because the balloon and the man and everything else is hanging freely in the air, we can say that the net external force on the system is zero. There will be gravity in the downward direction, but there will be upthrust because of the air around, and that is what makes the balloon go up in the first place. So the vertical force is balanced, there are no horizontal forces, and in fact even if there are horizontal forces, it doesn't matter because we are interested only in the motion along the vertical axis. Vertically there are no net forces, and I can think of the man and the rope and the balloon as one system. And when I take them as a system, the force of interaction between man and the rope, or the rope and the balloon, it becomes immaterial, and I can say that delta y center of mass, since F net external is 0, therefore acceleration of center of mass is also 0. That means acceleration of center of mass along y axis is 0, or maybe straight away I can say velocity of center of mass is a constant, and because it was initially 0, it will be 0 forever. That means the displacement of the center of mass is going to be 0, and when I write the displacement term, there will be three parts, x, y and z. So I am only interested in the y part. So delta y of center of mass is 0. So what I say is, let in the process of man climbing up, the balloon move down by a distance y. So that's what I have assumed. Now what happens? If the man climbs up a distance L, his y coordinate increases. I am taking plus y in the upward direction. So let us say that the upward axis is the positive y axis. And the equation that we are going to get now is mass of man times the displacement of man plus L minus y, plus L because he climbs up, and minus y because the balloon itself goes down by a distance y. So by virtue of being associated with that system, he also goes down. And then you have mass of balloon times minus y, and all that will give you a 0. So therefore y will be ml divided by big M plus small m, and the sign here is plus, showing you that you have assumed y in the correct direction. So that's it, very simple enough problem. Let's go over to the next one, people. The next problem here has got a say a railroad car on a frictionless track. So you've got a railroad car like this, and it is on a frictionless track. The track itself is shown here in red color. There is no friction there, mu is 0, and there is a person standing on this car on the left end. Let us say this blue person. The mass of this person is small m, and the mass of the railroad car is big M. And at a certain time, the man starts walking towards the right. So at a certain time, man starts walking towards the right. Now, as a result, the railroad car recoils. As a result, a railroad car recoils with a speed capital V. Find out the speed at which the man started walking with respect to the car. Find out the speed, or find out the speed of man with respect to the car. Yeah, so one thing to keep in mind intuitively is this. Your formula should confirm your inherent intuitive bias. Let us say the man is lighter and this railroad car is heavier. Then I know that for the railroad car to recoil with a certain speed, man should be moving at a faster speed in the right direction. So the final formula that you get, if you put certain conditions that the man is lighter than the railroad car, you should get that the speed of man is greater than the speed of the railroad car. Something of that kind, You will be able to check your final answer at least. But even otherwise, we should be able to get the answer. Even if you don't perform that check, we should be able to get to the answer. So let's see. Let us say the speed of the man with respect to the car is u. Let's say speed of man with respect to the car is u in the rightward direction. And because of that, we know that the car is going to recoil in the backward direction. Let us say the car recoils at a speed capital V. So the car recoils at a speed capital V in the backward direction, and this is with respect to the ground, clearly. This is with respect to ground, and the man here has got a speed u. This is with respect to the car. Now let us try to solve this problem in a ground frame. So let's make an observer stand here somewhere outside. So this observer O is the ground frame observer, and this observer is watching this entire situation. So before the man started moving, this observer said that the total momentum of the system is 0 because the man isn't moving, the railroad car isn't moving, and then at some moment the man started moving and the railroad car started moving backwards. But then this man will say that there are no external forces. If I take the man and the railroad car as a system, then whatever the forces the man is applying on the railroad car or the car is applying on the man, they become internal forces. Externally, the ground is frictionless, so I don't have any other force along the x-axis. So along the x-axis, if there are no forces, no external forces, then I should say the net external force is 0, acceleration of center of mass is 0, the velocity of center of mass must be a constant, and in this case, of course, it will be 0 and 0 before and after. But I can say that if the velocity of center of mass is 0, then if I try to find it out, I can equate the initial velocity of center of mass to the final velocity of center of mass. And I showed you in the previous class that that equation leads to conservation of momentum. So this guy will try to write some equation for conservation of momentum. He will say P initial, and let me do that here itself. P initial is equal to P final, where P initial is 0. And what is P final? So mass of man times velocity of man with respect to ground, and that is what we need to figure out. So velocity of man with respect to this observer O is velocity of man with respect to car plus velocity of car with respect to O, and velocity of man with respect to car is u I cap, and the car with respect to ground is minus v I cap. So you will have u minus capital V and you will have the mass of car times minus v, and what you are going to get is mu is equal to big M v plus small m v, or u is equal to big M v, or I can take that v common, so big M plus small m times capital V divided by small m. And you will see that the man will always have to walk faster than the speed at which the car recoils from the ground frame, because you see that the numerator is greater here. So that's how we get to the answer. Any issues with that, people? So the other way to do this problem could be if you assume the speed of the man with respect to ground instead of with respect to car. So let us go that way also. Let's say that let speed of man with respect to ground is some u naught in the rightward direction. So now a ground frame observer, what will he say? So this guy is the ground frame observer. He sees the railroad car recoiling backwards with a speed capital V, and this ground observer sees this man move forward with a speed u naught, where both the speeds are with respect to the ground. So what this guy says is that again the momentum should be conserved. So he says P initial is equal to P final. So since P initial is equal to P final in the ground frame for this man plus the railroad car system, so therefore 0 is equal to small m times plus u naught plus big M times minus V. Initial momentum is equal to final momentum. This will give you u naught is equal to big mv by small m. But now you want to find out velocity of man with respect to car, and that will be velocity of man with respect to ground plus velocity of minus velocity of car with respect to ground. So I will use this formula, and I'm going to say that velocity of man with respect to the ground is big M V by small m I cap minus velocity of car with respect to ground is minus V I cap, and you're going to get big M V by m plus V, all that I cap, and you're going to get big M plus small m times V by small m times I cap. So you will still get the same answer as the previous one, big M plus small m into V by small m, if you have taken all the variables properly. So you can still do it this way by assuming the speeds with respect to the ground and solving it. Now if you had to find out the speed of the man with respect to the ground, then this would be an easier approach, because you will get the answer here itself, u naught is equal to mv by m. But if you had to find out the speed of the man with respect to the ground, then the first approach will be longer, because you have found with respect to the car, you need to now transfer it to ground, so there is another step involved. So based on what is it that they want, you can assume a certain speed, and then you can later on change speeds according to the law of addition of velocities,